Okay, AP Physics 2 time. We're going to check out the photoelectric effect here. Just real quick, kind of a brief overview of it. Essentially, for the photoelectric effect, you take two plates separated by some distance, and you basically, for this experiment, hook them up through an amp meter, and technically a battery if you want to do the experiment, but we're really just looking at the amp meter here. And what you'll do is you'll take a source of light and shine it at the plates. Now, previous thought regarding light and its energy was that the brightness or the intensity of the light is what gave it its energy. But with Max Planck and Einstein, after he took Planck's idea and kind of ran with it, Planck's idea was that the energy given out by a photon of light was actually quantized. And it was actually given by the equation E equals h times the frequency, where this h here is Planck's constant. Planck didn't believe it was anything that important. He just thought it was kind of a slope that came out of the equations. But it is 6.626 times 10 to the negative 34 joule seconds. That's Planck's constant there. Kind of a very small number, but very useful number. As it turns out, what actually happens is Planck is right despite a bunch of scientists thinking he's wrong. And Einstein, as a result, is right with his photoelectric effect. And it's not the brightness of the light that is able to kick electrons across the plate to be able to read them. It's the wavelength or the frequency of that light, because frequency gives us some energy here. And as we dial up the frequency, we get shorter and shorter wavelengths. So we go from red to violet light, and then into X-rays and UV, and all of the high energy ones. Whenever you do that, you not only are able to kick the electrons out of this kind of salt plate here, but you actually give them more kinetic energy. They're able to zip across the plate faster and faster. And there's a wonderful PhET lab that goes over this if you kind of want to look at it. It's a Java applet, but if you look up PhET photoelectric, it's a wonderful little demonstration for that. Kind of shows you, based off of the color of the light you're pushing through or you're shining onto the plate, how quickly the electrons go. The only thing the brightness actually does is how many are you kicking out. So if you have a very, very dim light, but it's a very, very dim ultraviolet light, maybe one of your photons of light will hit and zip an electron across the screen very quickly. But if you increase the brightness, you're still going to get the real quick electron, but you can just have more photons striking, so you have more chances for this energy to allow the jump there. So you'll just get more electrons zipping across. They'll still have possibly the same maximum kinetic energy there. In the end, what we can say with the photoelectric effect is that HF, Planck's constant by the frequency, the energy that we're shining on, is equal to some kinetic energy plus some amount of work. And this amount of work is the work that it actually takes to remove the electron from these plates here in order to get it to jump. Because that electron, remember, is stuck within its orbital shells. We need to remove it. Now, just as a brief side note, sometimes this work function is designated as phi, depending on just what book you read. So be careful about that if you kind of get confused there. It's just photoelectric effect. But what we can actually do with this photoelectric effect is kind of take it one step further, and we can say that HF here is equal to some kinetic energy max plus some W naught. And this W naught is the work function minimum. It's the minimum requirement, the minimum amount of work in order to remove an electron and bring it across the plate. So if you've used the minimum work to remove the electron, then, well, the rest of your energy is going into kinetic energy to move the electron itself. Okay? So this is a very, very important equation right here for the photoelectric effect. Very, very, very useful. We can actually turn this equation into some other stuff if we kind of look at it. If we rearrange things a little bit, we can actually see this equation can be written as the kinetic energy max equals HF minus the work function. And this is actually a great equation once we have it, because it allows us to graph in a very, very interesting fashion. If we're able to graph the kinetic energy we get out of our electrons as they go bolting through the plates, what actually happens here, if we look at this, if we're able to map kinetic energy as a function of frequency, what we actually have is y equals mx plus b, where our y here is the kinetic energy. Our slope of whatever we're going to have here is Planck's constant, and since that's a constant, we're going to have a linear line. Some x value that's changing, and our b is actually going to equal minus omega, or w naught. So we actually see here from our values is that we're going to get lines that start below the x-axis due to the negative in the work function. They're going to increase, and what we're going to see here is that, like I said, that is our work function at that point. We're going to see at this x-axis, or this x crossing here, this is what we call F naught. It is the minimum frequency required to actually eject an electron. Because if we're at this frequency, we can see that our kinetic energy is 0. But if our kinetic energy is 0, that means that HF is equal to the amount of work done to release an electron. So that's the minimum frequency required to release an electron there. And looking at this line, we see that m, the slope, is equal to Planck's constant, 6.626 times 10 to the negative 34. And if we had, possibly different setups here, we could have a sodium bridge, we could have a calcium bridge. They're all going to be same parallel lines, but they're just going to have different work functions. It's going to be easier, harder for an electron to be kicked out of those setups. So they're all going to have the same slope, Planck's constant, and this is why Planck originally kind of thought we had just a slope effect here from some other experiments as well. But these just kind of shift up and down there. So that's a really, really cool graph. It's something that, if you haven't seen, definitely check it out. It tells us a lot of information about the minimum frequency we need, and it also tells us a ton of information about the work function itself. So definitely worth looking at that graph for a photoelectric effect. Very cool stuff there. But that's kind of the photoelectric effect in a nutshell. With that, we can be finished with it. Pew, photoelectric effect. Learn about it every day, forever.